Now, to calculate power with phasors, we have to use what we call the root mean square value of the quantities rather than the peak values, or we'd get too much. We would apparently have too much power. So the effective value of a sinusoidal quantity is going to be the peak value divided by the square root of 2. That's for the waveform of a sinusoid. Other waveforms have different constants to define their RMS values. And accordingly, the current phasor in RMS would be the peak value over the square root of 2 as well, because it's also a sinusoid. Now we can use the RMS values whenever in fact we really should always use the RMS values when we calculate power with sinusoids. Let's look at a simple phasor circuit example then. When we worked with DC, there is only one kind of power, just simple, real power. We could take the voltage times the current, and that was it. That was the power. Well, now it's a little bit more complicated because we have three kinds of power now. We have the apparent power, which we call S, and we have the real power, which is the same, that's P, that's in watts, and we have a new one that called the imaginary power or reactive power that we use Q for a variable. The way to calculate the whole thing, the complex power S, would be to take the voltage, phasor RMS voltage, times the conjugate of the phasor RMS current. Now here in this notation, I'm not using the little tildes anymore, and the bar across the current means that it's the complex conjugate of the actual current. Okay, so let's figure out what the values are here. We know the voltage in this problem is 500 at 0 degrees. Now that's an RMS value, and it's at 0 degrees to make the problem a little simpler. And the impedance is a 20 ohm resistor and a J15 ohm inductance. Now we're going to see how much complex power this load will take from the voltage source. To get the current, we will divide the entire loop impedance into the voltage. So 20 plus J15 divided into 500 will give me 20 at an angle of minus 36.87 degrees. Now, to calculate the power from this, I would need to take the complex conjugate of this current. The current is 20 at minus 36.87 degrees. Its complex conjugate will have an angle of plus 36.87 degrees. And if we take the product of 20 and 500, we get 10,000. So the apparent power magnitude is simply 10,000. But as a complex number, P plus JQ, we could say it in polar form as 10,000 at 36.87 degrees, and that will be in volt amperes. On the other hand, we have in rectangular form 8,000 plus J 6,000, also volt amperes. The 8,000, however, can be set aside and said these are in watts. 8,000 watts, so that's the real power, or you could say 8 kilowatts. And the imaginary power is Q, which is 6,000, but they're not watts, they're VARs, VAR. So the real power is 8 kilowatts, the imaginary power is 6 kilovars. The apparent power, which is simply the magnitude of all of that, another way to put the apparent power is that it's the magnitude of the current times the magnitude of the voltage. And that will be 10,000 volt amperes, or we could just say 10 kVA. The last thing about power here is the power factor. And that's the ratio of the real power in watts to the apparent power in volt amperes. In our case, that will be 0.8. And that we would say that that is a lagging power factor, and the reason is that the current will be lagging behind the voltage here, and that's by 36.87 degrees. Another way to define the power factor is that we take the cosine of the angle between the voltage and the current, and that will be also be the power factor. Many engineers would say that this power factor is 80%, and it would still be lagging, of course.